method of manufacturing carbon fibers, what we are going to discuss here is melt spinning or melt extrusion. So this is how the basic setup looks like. So you can see that this is an extrusion process. You know what is an extrusion. You melt a polymer. This is typically used for polymers and plastics. You basically melt a polymer and then you give it a certain shape and then you cool it down. That is the extrusion process. So you have a certain extruder. But the only difference is that if you're making plastic bottles, you have a different kind of mold for it, or you're blowing air inside it. You have different types of shapes, different types of molds. What kind of mold will you have for making fibers? So what you need to have is something known as this spinneret, which has nothing but a lot of capillaries, and then your material flows through it and you get fibers. This is the basic principle, and so this is a very simple process, right? This is just melt spinning. So this is performed for a number of especially petrochemical precursors such as pitches, and you can also use it for melted polymers. Okay, so let me just detail these steps again. So first of all, what you do is you melt your material, whatever is your polymer or pitch, above its glass transition temperature. Now, glass transition temperature is a very important concept. What is glass transition? I think we also briefly talked about it during photolithography lectures. Glass transition temperature is the temperature below which the material behaves like a glass. So above this, the material is sort of melted, or it is not. I don't even know melting is the right term that we should use for polymers. It is not. It's little bit the flow of fluids. Or flow of chains or the molecules of polymers has a slightly different mechanism compared to other, for example, melted metals. And this is what makes polymers very interesting. So there's entire polymer chemistry, polymer engineering courses. You can learn about the properties of polymers. But there are a few properties that we are definitely going to discuss here because they are important for fiber fabrication. One of them being the glass transition temperature, and the other one is what is known as viscoelasticity, and we are going to separately learn about these techniques because viscoelasticity becomes important for both melt spinning and electrospinning. So any kind of spinning techniques when you want to pull fibers. If you think about it, what is the property that you need in any material to be able to pull fibers? You need the material to be elastic to some extent, but at the same time carbon is hard and brittle, but the polymer that we use for spinning, they need to be elastic. But is it just elasticity or there is something else? Because we also don't want something which has no viscosity whatsoever for a reason. Okay, so we'll talk about these properties. The first thing we do in this setup is we heat the material above its glass transition temperature. Now that becomes sort of processable material. So now you can process it. Now you can pull fibers. How do you do that? You pump from the extruder, you pump this polymer into or pitch into what is known as the spin chamber, which basically removes. So first thing you need to do is you need to remove if there are any particles. Because if you have any particles, in the case of fibers, they can be catastrophic. You can, if between the fibers you will get these, bulges because of your crystals, and that might also mechanically damage your entire fiber. So first thing is that you need to remove if there are any particles. Now particles, that does not necessarily mean that you have impurities. Sometimes you may also have certain particles of the polymer itself. So it is basically the polymer that is still not, still does not have a free flow. So you need to remove those kind of sort of bigger chunks of material. So you will pass it through some filtration unit, and after that what you have is this spinneret, what is known as the spinneret, which is nothing. So I have also shown a cross-sectional view or the top view of this spinneret. What do you have? You have a lot of holes, and these holes are basically capillaries. Through these capillaries your polymer can pass. So this is basically the idea. Now you will of course have sort of very high chambers. So you will collect the fiber somewhere in the bottom. This distance is where you also want to cool down your fibers. So what you do is, number one, you can do quenching. So you can basically just cool it down. So you may have a cooling chamber. What will happen when you cool down the polymer? Then now it becomes now that temperature is below its glass transition temperature. So now it will become hard. And that is what you wanted, so that once you get the fibers, you don't want them to break further, you don't want them to change their shape further. What you want is, you want to make them glass like, you want to make them hard. So you can do the quenching or cooling, or you can also perform this cooling just by air. So you can blow air. That will also help in, it will help your fibers to stay away from each other, not sort of agglomerate or not form one big chunk of polymers. So this needs to be done very soon after they come out of the extruder, so that otherwise they will stick to each other. So you need to basically do quenching or air cooling. So in these kind of industrial setups, you will typically have a cross flow of the air for cooling the fibers. And as you can see at the bottom, you have a fiber collection unit, and typically you are winding the fibers. So you have these fiber winding units, and you can immediately, as soon as they dry up, you can collect them, and that is how you perform the melt spinning process. Okay, now as already I mentioned that this is commonly used for pitch, but you also can use it for melted polymers. Why I'm saying this? Because there are you will say that polymer should always be melted when you're performing any spinning. Yes, it should not be, but the term melted is not necessarily correct, because they can just be solutions. They are not, melted is something when you melt a solid, but you can also just have solutions that are liquid at room temperature. So those kind of polymer solutions, you will rather do electrospinning with them rather than melt extrusion. Melt is specifically for melted polymers. Now, these kind of polymers typically that are fabricated using this process will have their diameters in the micrometer range. You will not get nanofibers using melt spinning. You can imagine that also for making nanofibers or very, very thin fibers, you will need to have very small capillaries, and then the surface tension of the capillary becomes very important. You have a viscous liquid and very small capillary, then it becomes very difficult to have very thin diameters. So typically these kind of fibers you will have in the 5 to 10 micrometer range, or even larger. So 5 to 10 micrometer is what you will typically get after their carbonization, or slightly smaller than that. The shrinkage patterns in the case of fibers are also different from what you have for bulk industrial carbons, because there you have much more shrinkage due to much more mass loss. Here you will have much more surface area, so your defects or byproducts can anneal out easily, and you don't get as much shrinkage as you would get for the in the case of bulk materials. And we are going to discuss also why does that happen. Okay, this is a picture of the coal tar pitch. I just took it outside somewhere on a hot day. You will see a lot of so just to again give you an idea of what is pitch, this is this highly viscous material that you get on the roadsides on a hot day. It's not very difficult in India to get these kind of pictures. Beautiful material. It's a very high carbon containing material. It has this beautiful shine, and it has very good viscoelasticity. You can already see, you touch it and you will know that you can pull fibers out of it. So this is one of the most common or one of the oldest carbon precursors in the case of fibers. So let us talk a little bit more about the pitch carbon fiber fabrication, pitch-based carbon fiber fabrication. So this is a process flow, because this is the industrial process used very commonly that you should know about it. Isotropic or mesophase pitch. You will take any type of petroleum pitch, and then you will perform the extrusion as I have shown previously using this spinning setup. Okay, now you have pitch fibers. What do you do with pitch fibers? Do you directly carbonize them? Now there is one more stabilization step in between. So this stabilization is performed in air. For isotropic pitch, you perform it at between 200 to 300 degrees and degrees centigrade, and slightly higher temperatures for mesophase pitch. Stabilization is typically performed to get rid of the undesired organic material, some of it at least. And you're performing it in air. That means you are open to burning those things out. So any volatile organic materials will typically burn out. Only the heavier hydrocarbons and those which are high in carbon content, they will stay there. So that is why you perform the stabilization. Also, the stabilization step leads to a little bit of cross-linking between your heavy hydrocarbon type molecules. So you then get less porosity in your fibers, and you get good quality, good solid fibers. So you need to perform this stabilization of pitch, and afterwards you perform your regular heat treatment. Now, when I say regular heat treatment, it depends what is the crystallinity that you want in your final fibers. So mesophase pitch will give you more like polycrystalline, almost polycrystalline graphite like fibers. But although they may have different kind of structural arrangements, these graphite sheets may not be as nicely, you don't imagine these polycrystalline materials that I have shown that, you have these random orientation. That is a possibility, but that is not the only one possible microstructure. So we are also going to discuss what are the possible, ordering, what kind of stacking of sheets that you get in these graphitic fibers. But that is only from the mesophase pitch. You can also get isotropic carbon from isotropic pitch. Okay, so first you perform the heat treatment at relatively low temperature, so between 800 and 1200, and you can actually also stop at that point if that is the desired carbon material. Now, in some cases, industrial applications, you don't really care for very high purity of carbon fibers, for example. Now, you can perform the heat treatment further. You can go all the way up to 3000 degrees, as in the case of graphite, and you can get really, really high purity of the fibers. You can also get much higher Young's modulus, good stiffness of the polymers, but of the carbon fibers. But is that what you need? Sometimes it's not the stiffness, but rather the flexibility, rather the tensile strength of the fiber. That becomes more important for you. Purity, how much purity is acceptable to you? Depending upon that, you will also need to see how much cost is going to be increased. Because 3000 degree heat temperature is very energy consuming. So if it is acceptable for you to have the fibers at slightly lower temperature, you might want to stop there. But if you definitely need very high quality carbon fibers, then you will go all the way to 3000 degrees, again in similar types of furnaces that you would use for graphite manufacturing. Okay, so this is the process flow of pitch-based fibers. Some important things about pitch is that most of the pitches have their purity between 90 and 95%. Little bit higher is also possible, but most of them have 95, let's say, % purity. They have this special property known as the viscoelasticity. As I mentioned before, we are going to dedicate some time on viscoelasticity, but briefly, the definition of what is viscoelasticity. So as the name itself suggests, this material has both viscosity and elasticity. Elasticity is a property of solid materials. Elasticity means if you deform the material, it will come back to its normal place as soon as you leave it, like a rubber band. And that is the elastic property. That is a property of solids. Viscosity is a property of liquids. This is the force, this is the resistance to the applied force that a liquid offers. So now this polymer type of materials or heavy hydrocarbons like pitch, these materials offer the properties of both solids and liquids. So they have both viscosity element and the elasticity element. How is that possible? You know that polymers have these long chain-like molecules. So you have hydrocarbons. Also in the case of pitches, you have hydrocarbons that are chain-like molecules, or in some cases sheet-like molecules. Now these chains can entangle. So they can form these very structures that are very difficult to open, so to say. They are entangled chain-like structures, but at the same time they may also have some chains that are floating or that are able to freely flow. Not all of them, but some of them. So you have partially solid-like properties. Similarly, in the case of semi-crystalline materials or in the case of liquid crystal-like materials such as mesophase pitch, what you have is, you know that there are certain parts that are crystalline. These crystalline parts behave like solids and they can offer elasticity, while the liquid-like parts will offer resistance to flow. So that is why you have a combination. And that combination can, by the way, be very complex. Not all polymers will have the same viscoelastic properties because, well, not all polymers are semi-crystalline, or not, the chain arranged, the size, the length of chains in different polymers is different. Some of them have very short chains, some have very long chains. So depending upon all of these factors, you will have different viscoelasticities in various polymers. But this viscoelasticity is very important in order to be able to pull fibers out of something. Because if it is a liquid, just a liquid, not elastic at all, if it has only viscosity, let's take an example of water. Difficult to pull water fibers, right? So that we definitely need elasticity. But since it is a liquid, we also need some viscosity. So we do need some liquid-like properties, because if it's a solid material, just a crystalline material, then also it's not possible to pull fibers out of it. So viscoelasticity is a very interesting property that pitches have, and that a lot of polymers also have. And in fact, you can also control the length of the chains. You can also control how much solvent you have in a certain polymer solution. So based on that, you also sort of tune the viscoelasticity a little bit for manufacturing fibers. Okay, now in the case of pitch-based fabrication or the melt spinning, you would typically also control the viscosity to some extent by the melting temperature, because here you are you know that you want to have a certain viscosity in your liquid, which is just optimum for giving the fibers, and also the diameters of the fibers can be controlled by this viscosity. So you can imagine that if your material has water-like properties, then you will not be able to pull fibers, but it's slightly thicker than water, slightly more viscous than water, then you are able to pull fibers, but they might be very thin fibers. Thin fibers, how long can they be? How long is their aspect ratio? What is the possibility there that we need to optimize? And then if you have these very viscous fluids like honey, then you can pull fibers, but those fibers, what is the minimum diameter you can get from these fibers? These are the things that are optimized for various the materials that are being spun. Okay, so in the case of pitch, we control it by controlling the chamber temperature. Okay, and then you, as I have already mentioned, then you perform the heat treatment under inert environment. That is done after stabilization step. Okay, you can also, if you need certain properties, for example, if you need very high crystallinity in your polymer, but you only have isotropic pitch available, you could potentially mix a few coke particles or even carbon nanomaterials, some sort of carbon nanotubes. These kind of additives can be mixed inside your pitches before the fibers are pulled out of it. But of course, you need to remember that you need to have an optimum concentration of the additive, because if it becomes too and also the size of the additive, because you remember that you were filtering out these solid particles. So if you then add bigger solid particles, then you will not be able to, then it will block the capillaries. So you need to have only very small additive, this in terms of size, but that is also possible. Okay, for all carbon materials, this is our golden rule. Higher the heat treatment temperature, higher the crystallinity, higher the stiffness. And when we say stiffness, we are talking about the Young's modulus. Okay, so this is also valid for your fibers, and this becomes a very important property. Of course, industrially important, because for many applications, what you need is good mechanical strength. So that is why, for same thing for carbon fibers, especially pitch-based fibers, the higher the heat treatment temperature, also that would increase the cost of the fibers. So this is basically a direct measure of the quality of your carbon fibers. So I told you that the microstructure of pitch-based carbon fibers, especially mesophase pitch-based carbon fibers, it's very interesting. Mesophase is more interesting because we have graphite crystallites. So we can have, here you see like these, what is 6 of them, possible arrangements of these graphite crystallites. One of them, the third one, is the random orientation. That is what you would expect from other types of pitches as well. So if you have isotropic pitch and you heat it up to 3000 degrees, you will get some graphitic content. But in that case, you know that the graphitic crystallites will be randomly oriented. Also, you will have some non-crystalline parts in between them. But if you also have all of these are, let's say, from mesophase pitch, you will get very highly graphitic material. You will have very small fraction of non-graphitic carbon in that. So we can call them graphite fibers. In fact, this term is also industrially used. You will hear the word graphite fibers. Be careful, sometimes industrial fibers, they are not really graphite, they are just graphitic, but the terminology, they call it graphite because that, graphite sounds more sophisticated and also more costly. So often the terminology is also used in a wrong fashion. Anyway, that is not our concern. For you, it is important to know what is graphite. So for you, it is important to know that if you have very high crystallinity, then you can call it graphite fiber, not graphitic fibers. Okay, from mesophase pitch, when you get the fibers, you can have these various arrangements of the graphite crystallites. So if you see the cross section, these are the pictures of the cross sections of the fibers. So the first one, you can see all these graphite flakes are randomly organized, radially organized. Okay, that these things will, by the way, depend on your on at what speed, what temperature, what type of pitch you process. So these are dependent on your manufacturing parameters as well as your carbonization parameters. So it will depend on what is the heat treatment rate, what is the ramp rate at which you heated these polymers. Also, what is the highest temperature, of course. Second one you see is this radial kind of, so you have these concentric shell-like structures. Okay, concentric cylinders, sorry. So this is the cross section. You have onion skin is what is the name that is used commercially, but this is the concentric cylinder type structure. Then you of course have the random orientation. You can also have these small flakes but flat, like, you know, on top of each other. They are trying to organize themselves, so they are just flat structure. Then again you can have radial structure but folded. So you have graphitic crystallites, but they are highly turbostratic. Turbostratic means they are not completely there. It's not an ABABA arrangement. So in the case of carbon fibers, when we talk about graphite fibers, even when we use the term graphite, we may not have the perfect ABABA organization. Here we call a fiber graphite when it has just a very high graphitic content. Even so, you have the large La value, large crystallite size. LC value is little bit tricky in the case of fibers because you do not have these perfect crystallites. So here in the case of random or organization, maybe there you can probably calculate. Okay, this is the crystal, the LC, the crystallite, the stack thickness. But in the case of radial or radial folded geometries or morphologies, you may not be able to calculate the LC in the same way that you did for other crystallites. The point here is the La value becomes more important, and the fact that you have a larger crystallinity and less very small to negligible, basically non-crystalline parts, then you will call them graphite fibers. Okay, so these, in some cases, in many of these cases, your stacks, your graphite sheets may not be perfectly organized on top of each other, or maybe you will have the stack thickness, but so each of these lines that you see here, that is not necessarily one single graphite sheet. It may be a small stack of graphite sheets. Okay, but however, they have certain curves. They are not perfect as in the case of HOPG, for example. Okay, now the last one that you see, line origin, that is something which you get if your spinneret, if your the from where your fibers were extruded, if that is not perfectly circular. So you may also have different shapes of the spinneret, and you sometimes intentionally do that because you want to have higher surface area. You see, if you have this kind of fiber shape, then you will be able to have more surface area in the fibers, so your byproducts will anneal out more easily. And also for whatever application you're using, maybe this is a better geometry. So also, other than these 6 structures, you can also have some other possible morphologies. Of course, if you change the shape of the spinneret, you can make it also flat ribbon-like fibers, for example. So there are many such options that are possible. Okay, now yeah, so these are some of the things that I have already mentioned. In the case of highly graphitic fibers, you have various possible methods of the stack organization. Okay, now typically the heat treatment is performed in all cases, industrial cases. You perform the heat treatment at less than 5 degrees centigrade per minute. That is your temperature ramp rate. That means how you increase the temperature. Okay, and then you will keep your material at the final heat treatment temperature for about at least an hour. You can also do it for several hours because that also leads to better organization. In the case of fibers, you need to understand whether or not high Young's modulus is important. So if you are using these materials for making certain structures, manufacturing purposes, often you need high stiffness, but not all the time. Let's say if you're making biomedical implants, what you may need is also a little bit of flexibility, so that when your tissue is growing on top of that, let's say bone implant, then the tissue is able to press it a little bit. And that is why you may not need very high crystallinity. But that depends on your application. Even in the case of bone implants, it depends on whether you're making the load-bearing joints of your body or other joints of your body, or you're making also a tissue implant, ligament implant or ligament template on which it can grow. So these are certain applications. The point is that you need to decide what are the properties in your fibers that you want, and accordingly you can perform the heat treatment temperature, at higher ramp rates, lower ramp rates, higher temperature, lower temperature, and so on. Okay, so yes, you can make fibers in the micro scale, you can make fibers in the nanoscale. In the nanoscale fibers we are going to talk later on. In principle, during the heat treatment, you should use slightly lower temperature, as I said, because the byproducts and defects can anneal out more easily. But if it is in the micro scale, still the effect of surface area is not that strong. When you have nanoscale fibers, then the surface area effect becomes very strong, especially when you go below the diameters, 50 nanometer diameters. So if you have a smaller than 50 nanometer polymer fiber, then the mechanism of carbonization becomes slightly different, and you may get more graphitization at lower temperatures. But in the case of micro scale structures, this effect is there, but compared to bulk structures, but still not so prominent that you can drastically reduce your heat treatment temperature. Okay, for further reading, there are a lot of books on carbon fibers, and they are very good books, very good articles. So you can, if you just do an internet search, you will definitely find several books on carbon fibers. I have mentioned a couple of papers also because I took some pictures from there, and I followed this, this book called New Carbons, and also this paper by Eddies. These are the papers that I have utilized. You can, there is a lot of reading, further reading about the microstructure of carbons and carbon fibers, and especially the pitch-based carbon fibers. Now, in the next couple of lectures, we are going to learn about electrospinning and also some properties of the polymers that are required for electrospinning.